Okay. So, hello everybody who are watching later. Just going over a quick review for what is going to actually be on this exam. Remember, your exam is going to be on Thursday. There's going to be one Thevenin's problem. Is it a Thevenin's problem? Either a Thevenin's or a Norton's problem. We're going to go over a Thevenin's problem today. So Thevenin's, Thev/ Norton's. There's going to be a complex emittance. Hello? I am going to misspell everything because I do not know how to spell. I am sure that I spelled that wrong. And then there's going to be a first order switch. And then there is going to be a second order damping problem. What does that mean? So what I mean when I say second order damping is it's going to be a second order problem, but you're not going to have to generate it from scratch. You're not going to have to say, okay, here's a giant circuit. What is the ODE? He's going to give you the ODE. You just need to know the properties of second order. And you need to know the properties of damping, which is going to be in your appendix of D1. And we're gonna work some problems today. We're gonna go through a complex emittance one, which is your steady state whenever you have your like sine or cosine source. And then you just solve the problem like you normally would, except there's imaginary numbers in there. We're gonna do a Thevenin's problem. And then we're gonna do a switch problem. And then after that, we're gonna do a second order example that I have. And then we're gonna work some homework problems on second order because we know that they're hard and we want to give you some extra help and guidance with those. So now any other questions with that? Good stuff. Of the three I said, which one do y'all want to start with? Okay, we can do 7 minutes. So we're going to just like keep this in the corner. Okay, so here's our question. We're pretty much just going to go through 2020, spring of 2020's second exam. I normally pick problems from random places, but I actually liked this entire second exam and it was pretty relevant. So that's what we're going to do today. So good. So we have our network, which is connected to this load resistor of RL. So it's asking for the Thevenin's equivalent of this network, and then express E Thevenin's and R Thevenin's in numeric form to get down here, and then use that Thevenin's equivalent to calculate the value of the load current. And then it says, for maximum speed and efficiency, apply the name. So whenever we think Thevenins, what should we think of? Exactly. Exactly. So we should think of name, and importantly, we should think of conductance. Name, conductance. We could, yeah, name and conductance. So before we even start this problem, we have some steps that we need to do. What do we need to do to this circuit? We need name, which is also going to be current sources. So this voltage we need to convert to current. And I'll go ahead and redraw. You know what we're gonna do? We're gonna do another piece of paper. So let's redraw this as a current source. What is that current source going to be? Yes, it would. Easy. So it's going to be 1 amp. So we're actually going to be getting all of my pens situated because I have a pen addiction problem. We're going to change both of those. That's how we're going to change it into a current source. We're going to take these two, and then we're going to change it into a current source in parallel with a resistor. What if we had a resistor? Then you would have to have all three of them. So it's a good question. If you had another resistor here, you would have to do this resistance. So if this was like 2, you would have to do 2 plus 1 to convert, excuse me. And so then it would be 1 volt divided by 3. And then this resistor here would be 30. Make sense? So you have to do basically. Yes. So pretty much the top and bottom, and then you add a third resistor. Yes. If that were the case, we would do that. Now it's gone. And then, so which way is the current source going to be facing? Up. And this is still 1 ohm. 1. Now I'm just going to keep redrawing everything. Oh, I shouldn't have written 1. So while we're doing this, we should also go ahead and convert everything to conductances. So 1 over 1 is 1, right? Let's do 1 over everything else as I keep going. So what about R2? Yes, we can just say 1 over 2.5 because that's going to not be a fun number. It's 0. Oh. Yeah. Just 0.4? Cool. Good stuff. And then what about this guy up here? 0.1. Siemens, yes. Siemens. It's hard writing S's, and you'll get to this in circuits too as well. Writing S's that don't look like 5s. So these are all S. And then this is going to be GMV2. And then I'm going to kind of do what Russell did as well. And do this over here. So I'm not going to connect them. The reason I'm not going to connect them right now is when we find the Thevenin's equivalent, we don't apply that load resistor as part of it. And that's because that load resistor can change, but we don't want the equivalent to change. If the equivalent changes, then what's the point of it? We want to have an equivalent up to those 2 points, A and B. And then from there, we can figure out any current that we want for the load to go through the load resistor. Because eventually we want the load current. So eventually we're going to find this current IL. This dot cam doesn't have a like brightness, it just has exposure, which is interesting. Doesn't have like a light. It's a weird little dot cam. But 1/2, 5. And then we have, yes, but we can keep that as 1 actually. Yes, because it's not going to be a part of the name. And so we'll just deal with that at the end. And we'll put that back in here. Then what next? So we had our node voltages right here, VN1, and right here, VN2. So what I also like doing, and you've been in with my office hours, VN1, let's circle all of the places that VN1 actually is. Because it's not just here. Is this VN1? That VN1. Let's just, for sake of clarity, let's just circle that. So that's all VN1, and same with VN2, right? That's VN2, right? That VN2? Sweet. So we have 2 nodes, which, how big is our matrix going to be then? Not bad. So whenever we see Thevenin's and Norton's, we're going to have to add something. What do we have to add? We're going to have to add something over here.
Right.
Yes, J not. J sub 0. So the reason that we're doing that, we add this guy over here. Let's make it circle.
You confirm this that it's an orientation
Yes.
to any value that's convenient for us. Gotcha.
Which the most convenient is 1. But then which way do y'all want it to face? It's either or. I dig it. I approve. So this is J naught. The reason that we're doing that is for interesting math reasons. Number 1, we're using name, so if we added a source, it needs to be a current source. We shouldn't add a voltage source for something that's all, like all of our sources need to be current sources. But number 2,
we eventually want voltage. So since we want voltage, can't see my colors. That makes me sad. So we want voltage, which is going to be our node voltages. We're solving for voltage in our name. So voltage is going to be, is it going to be VN1 or VN2? Now what about the other side? So it's going to be the difference from here to here. What's the voltage down here? What's a current? So this is a trick question. Down there is ground. Down there is 0 volts. So this is going to end up being VN2 minus 0, which is just VN2. But if you remember that pentagram problem, it's technically the difference from here to here. So if there's a voltage down here, like if this wasn't 0, you need to remember it's this point minus this point. Yeah.
Why is it in?
So we're looking at the point from here to here. What is the voltage at this point? Yes. It's whatever, and that's why we drew the big circle, right? So we're saying all of the voltage in that circle is VN2. So since we need at that node, all it's going to be is just VN2 minus 0, which is VN2. And then, so we add a current source because whenever you turn off a current source, what is a 0 amp current source? It is an open circuit. And that's, I say that a lot. I try to drill it in because it's so important. Because so think about a wire, right? Think about just a connection. If there is no current flowing through it, does that look like a wire or an open circuit? If there's no current, that means that there's nothing there. There's no connection because there's no current. That's why it's an open circuit. Same with 0 volts. If you have a wire and you tried to measure, is there a voltage difference over this wire? There wouldn't be. And so that's why 0 volt voltage source, a turned off voltage source, just acts as a wire. And that's going to be really, really important, especially for your switches. So back to voltage source, the other really interesting thing, and it blows my mind thinking about the math of it, is we need our Thevenins. So we have our lovely Ohm's law, right? V is equal to IR. No, that's not right. Yes. So if we want resistance is equal to V over I. So we already said we know what the node voltage is. It's VN2. But since we're putting a current there, can we just say that the resistance is that node voltage divided by whatever that current is?
Apparently one, right?
Mm-hmm. Yeah, so since we're choosing to divide by 1, it's just VN2. So we add a current source here to manipulate Ohm's law and use that to get our Thevenins. So now we are ready. This is all set up. We can go ahead and throw these numbers into our matrices. So we said 2 by 2. So first node, what are all of the conductances touching that node? Sounds like 1.5 to me. 1.5. How many are shared between VN1 and VN2? Is that going to be positive or negative? That is the definition of name and name. Everything that is not the diagonal is gonna be negative. Yeah, I know it's been a minute.
Yeah,
Everyone's been looking at switches so much.
yeah.
So negative 0.1, negative 0.1, because shared between VN1 and VN2 is the same as shared between VN2 and VN1. Lastly, how many conductances are touching VN2? What's that value? 0.6. Bingo. So now this is going to be multiplied by VN1, VN2. This is going to equal our sources. So this is going to be our J's. It's not how you're supposed to write it, but it's J's. I wrote J apostrophe S. That shouldn't be what you call it, but I'm bad at notation. That's why I will never count off for y'all not doing notation right.
What's it supposed to be, version?
It's like our J matrix, and then it gets separated into JI, JB, and J naught. But we missed a step. We need to write an equation for V2, which I didn't even write where V2 is.
It's at the.
Oh, yes, you are so right. So another color, if you can even see the color. So we, from up here, from here to here, this is V2. So what is the voltage V2 in terms of our known voltages?
Well, you want to subtract 0, which is VN1.
So that would be, you'd be correct. However, we're trying to write it in terms of our variable. Sorry. I get distracted. We're trying to write them in terms of our variables because the goal is to be able to separate it out into a form that looks like this. So if we're trying to write it in terms of VN1 and VN2, let's say again, how would we write this V2? So that would be the voltage from here to here. That would be that voltage.
VN1,
It's just VN1.
because we're subtracting from the ground, right?
Exactly. It is just VN1. So we'll write out an equation for V2 and always for me and for your grade, write out your equations. I want to give you all as much partial credit as I can, and so throughout I'll say how I can give you credit, how you can word things. Definitely write out your equations. Say stuff like this. And then GM is equal to 40. Wow, okay. Where GM 40. So we can do it symbolically still. So let's say how many currents are going in and out of VN1? And what is that? Oh, also one. Yeah. Here. That's on me. That's my bad. Just one. Now, what about VN2? Couple more things. So this 40 Siemens times VN2, VN1, is that going to be positive or negative? That's going to be negative 40 VN1. And I went ahead and plugged in numbers. Do you want me to instead write GM V2? Or is this good? Okay. Okay, cool. So yeah, negative 40 VN1.
It's
And then-
negative, it's going out of the node, right?
Yes. I've always thought name is a little more intuitive with that. If it's entering, then it's gaining current, so it's positive. If it's leaving, it's losing current, so it's negative. And then I did plus J naught. So we are going to separate this out into 3 matrices. We're going to do J I, so independent, J D, and J naught. Hello. So for our independent, what do we got for independent? Just 1. 1, 0. What about JD? We'll write it again. And then J naught. We can either do 0, 1, or we can just do 0 J naught. Up to y'all. Cool. So now we have one more step. We're very close. This is a much easier problem than the pentagram. What do we need to do with this guy right here? We want all of our variables to be on the other side of the equation because Vn1 is essentially our x. Just like algebra, we want to get all of our x's to the other side of the equation and have all of our nice pretty numbers on the right side of the equation. So we want, for us to be able to subtract it, we need this to look like this. We need it to be a 2 by 2 matrix times Vn1 and Vn2. So how can we write this? What's it going to be? Where it's a 2 by 2 times Vn1, Vn2. Close.
Here, there, negative 40.
There you go. So it's 0 because on the top, because on this loop, there are no either of those. And then second, this is Vn1, so there's negative 40 times Vn1, negative 40, and 0. So then what we're going to do is we are going to draw a big arrow over here. Say subtract. And then what is that minus that? Pretty simple, right? Everything stays the same except 1.
Negative 40.
So it's going to be negative 0.1 minus negative 40. Yeah.
Is the V2 or control, man?
Yes.
Okay, so that's why we have the Vn1 next to the negative 40. Right?
Yes. So V2 is equal to Vn1, which is, it's tricky.
Yeah.
But it needs to say n. So if you see just V2, you're gonna have to rewrite it in terms of Vn. So like you said, 39.9 and 0.6. Weird choice. So then this is equal to our 2 matrices. So we have our 1, 0, which is our Ji, plus 0, 1 for our J naught. So like we said up here, we said to get the voltage, we're just going to say what is the difference between V, N2, and ground. So do we need our J naught for that? Okay, so to find V Thevenin's, we are going to set J not equal to 0. And then to find our R Thevenins, what are we gonna do? And what else? Exactly. So let's solve those in our calculator. Can we do that? Just solve for V Thevenins. And then for V Thevenins, we're going to solve for both of them. And then what is our answer for the V Thevenins going to be? Going to be VN1 or VN2? For the V Thevenins here. So, yes. So go ahead and can someone do that in the calculator?
That's negative 8.15.
Negative 8 point. What was it?
1.951.
0.815.
Oh, no, it's 8.1595. It's 8.15. Then 951.
Thank you. That was rough. And then, so do y'all understand why I did the VN2 for that? We look back up here, we're looking from this point to this point, which is VN2. So we solved and we got 8.15951. Yes.
First or the other name?
Mhm.
So why just come on over? So I'll just do the inverse of one. The inverse of the first one. Yeah. Okay.
Can one of y'all do me a huge favor and run to IEEE and grab my calculator? Because I left it charging in there. And Mike or no, thank you very much. Because I did, it was dead, and then I was like, oh, I'll charge it, and then it slipped on back. So I was talking with Russell upstairs. But I'll go ahead and show what it'll essentially be. So it'll be our 2x2 -1 times equal to B. So that's what it's going to be, but I'll show you how to do that in the calculator. And then we're going to do the exact same thing for our Thevenins. We're just going to do, instead of 1, 0, we'll do 0, 1. Yes, that is precisely correct. Yes. So
That's from being two of the subheads, right? So we can.
yes. And then we'll do the exact same thing. Because we're going to keep everything else the same. Like we're still, that's a very important thing. Whenever we solve for V Thevenins and R Thevenins, yeah. Thank you very much. We still have the subtracted value. No matter what, that dependent matrix will always get subtracted over, regardless of if it's for V or R. So then the only thing we're going to change is we're going to do 0 and then 1. And then now that's what we're going to get. And which value are we going to use for our R Thevenins? We're still going to use VN2. Because we're still looking at VN2.
Okay.
We're looking at the same place. So we're going to use the exact same value. So now our R Thevenins is going to be 306.748 milliohms. So, questions, comments, concerns? Do y'all want me to go over again how to put a matrix in a calculator? Speak now or forever hold your peace.
Do it another way.
Ooh, yes, there's also the RREF. I can also go over that. Or I can move on and we can keep doing other problems.
Can we move on?
Okay.
No, but wait, before we move on, can
Yeah.
you explain this part again? Why we said J nine, which is zero, because we didn't, I don't know, like,
Yes, so we look back up here, right? Oh, and we're totally not done. There's another part of the question. Read the question. It messes everybody up. I do the same thing, obviously. So whenever we're looking at J naught, all we are trying to find is the open circuit. We are trying to find the difference from here to here. And then when did we say a current source is an open circuit? So, yeah, we set it equal to 0 because we don't want any current flowing. We want the open circuit potential difference. So what that means is we don't want anything flowing. We want just the voltage difference. So that's why we set it equal to 0. And then for the resistance, it's kind of weird that we set Ji equal to 0, but I don't know if you really taught Thevenins and Nortons from like the brutal way to do it. The brutal, not Thevenin, not Maven name way to do it is you turn off all of the sources. Not the dependent sources, those still need to be on, but you turn off all the independent sources, which means you set them equal to 0. And hence we set our independent equal to 0. We basically are just turning off this 1 amp. And by that it goes away because it's equal to an open circuit. So that's why we set that equal to 0. That's why we set the other one equal. Good stuff. Now we have one more task. We need to find the load current with 1 ohms. How do we do that?
It's divided by the row resistance.
Let's go ahead and draw it. So we have a voltage source and we have a resistance. We know what that resistance is going to be, right? Y'all want me to do 306 milli or just 0.306?
okay.
136.
Okay. And then for this, it's going to be 8.159. Is it going to be pointed up or down? For voltages and currents, all a negative means is it's pointing the other direction. And the only other step is we have 1 ohms because that's what it said. And now we just use our lovely, lovely Ohm's law, where the current is equal to V over R, which is equal to 8.159 divided by 1.3068. So what is our IL going to equal? Like 6.24 or 4. Do 3 decimal places today. Not going to be amps or milliamps. Yep. Good stuff. and we just finished our problem. How do we feel about that? Not too bad? There's a chance that it's going to be Nortons instead of Thevenins. Or yes. And all that would mean is we do the exact same process, except it's mesh current and we have E naught. But it's the same of if we find our source. So if we find our Norton's current, we're just going to set the independent, we're going to set the E naught equal to 0. And if we want to find the R Norton's, yes,
For that one,
yes,
if the power is flipped around, for the result, do we have to put the arrow pointing in different directions? I think we indicate it in the circuit.
like this.
This
Yeah.
point, like instead of up and down.
And this also should be negative. We forgot that. Because we specified that our IL is going down, but this says that our current should be going this way, right? So this should be negative. And yeah, you can just keep it positive and switch the polarity like I did, or you can just say -8 pointing up. I'm okay with either as long as it's right. Yeah,
So we pretty much added the load resistor to the equipment.
yes. Yeah, that's all we did. We just did the total resistance.
Converted the constructor for, when did it be back to resistance?
So that is a good question. You're good. Pretty much the R Thevenins doesn't entirely have to do with these conductances. Because remember, the way that we got Thevenins is V over I. And neither of those things are conductances. Intuitive, right? But we're using the conductance to find the voltage. And then we use the voltage to find the resistance. If we wanted the conductance, all we would do is I over V. But then, yes.
That's
Yes,
the opposite.
because in that one, right, we solved for I.
Then fall for.
Exactly. So Norton's will ask you for your current and then a equivalent conductance. So it'll still be whatever we find divided by 1. That's why we keep it 1. Make sense? Sort of, kind of, good? Good stuff. So let's move on. This one, we're gonna do, this one should be relatively simple. It just looks scarier because it has squiggly lines on it, aka an inductor. And so yes, that is EG of T. EG of T is equal to 10 volts times cosine of 500 T plus 30 degrees. This is an RLC network. However, you're not going to solve it like a second order because it asks for the sinusoidal steady state. When you think of that, you should think sines and cosines instead of differential equations. Differential equations is for your impulse response. Which, do you know what that means when I say that?
Sounds familiar.
So what an impulse response is going to be is if you hooked up an element to a scope and you either had a charged or an uncharged inductor or capacitor, it would on a graph look like, if it wasn't charged, it would go like this, right? It wouldn't be a linear thing. So your impulse is your equation for this line. So, because it's not an easy, like it's not a linear equation, obviously. So the equation of this line is your IL of t. That's what we're going to solve for when we get to our switches. And then tau is 60% time constant. So then this is going to be your tau. And then the difference to get from 10% to 90% is going to be your time rise, is equal to tau ln of 9, which I will go over again whenever we get to the switch problem. This is what impulse response is. Sinusoidal steady state is say, okay, instead of just applying a DC current, we're going to apply an AC current. Because the AC current is constantly moving up and down, it's never going to fully get to a straight line. It's never going to be fully charged or fully discharged. And if it is, it's very, very short time. So whenever you see a sine, your end is going to be a sine wave. But say this is your sine for your like AC, your inductor current might be something very, very different. How long has that been there? Okay, cool.
Like, you wouldn't know.
Facts. Big, big facts.
It's the red side.
Um, Okay, that's good, right? We're good with that? Okay, cool. Sorry. So basically, we're gonna find this current. That's what we're solving for right now. And that's kind of the difference between your impulse and your steady state. That makes sense? Sort of. We'll do the problem and then you'll see why it's different. I had a student and we joke about it now. He saw RLC and he freaked out. He was like, second order wasn't going to be on the exam. What the heck? And we were like, no, hold on. It's sine. It's not the same. So if you see RLC, this isn't that bad. So all we're going to do here is whenever you have sinusoidal steady state. Okay. Apparently that's hard to say 3 times fast, but all that means is we're going to look at it, put everything into impedances and solve it like you would any other circuit. So whether it's you think the easiest is MAME or NAME, or for this one, there's just one loop. So could we solve it just like it's a normal one loop? Indeed. So let's do that. One more thing that we're gonna do is how can we write this in a way that doesn't have cosine? So you can do the rectangular form or the polar form. I personally, when it comes to this, prefer polar form because polar form is a phase angle of theta, right? So when you look at this, it directly corresponds to this is A and this is theta. So this literally just means that what would this be? Tell me what the polar form is it. Yep. That's simple. That's the imaginary form. What is this 500? Mhm. Angular frequency, otherwise known as omega or fancy W. And your omega does not change. Your omega, whenever you put it back into this form, will not change, and it's also not in your polar form. So it's easy, right? What it will affect is going to be when we put these values into impedances. We're going to see that this is just one loop, right? So we have voltage. Would it be easier to have impedances or admittances? We want everything in ohms. So ohms are 9 times out of 10 easier to work with. The only times that you would ever put everything into admittances is if you're doing name. So if you see a network like this and it's set up for name, you're going to put everything into Y because Z is impedances, which is equal to ohms. Y is admittance.
Are we gonna be doing anything with reactances from the sequences or susceptances from admittances or not really?
Not in this class.
Okay, got it.
You'll get a little bit, like a tiny bit into reactance, but what is reactance? So reactance, which is X, is just basically the coefficient of the imaginary number. It's just the imaginary number without the J or without the I. When you have it in admittances, or impedances, it still has that imaginary. So X is just take the imaginary out of it. That kind of makes sense, but don't worry about it. Don't worry about it. What we need to know is Z and Y, and those will not go away in your career or in your degree of electrical engineering. So, like I said, we're going to use impedances because ohms are easier to work with whenever it comes to just a loop. So now we need to remember, we need to make all of these into impedances. So what is the equation for L impedance?
It's J omega.
I'm gonna J to the
Mm-hmm. J omega L. And then what about capacitance?
Negative J
WC.
omega.
Mm-hmm. Which is also equal to 1 over J omega C. If the signs mix you up, I would just recommend doing that because 1 over J is the same as negative J, which nobody explicitly told me that, and I didn't realize that.
The
An identity, yeah. So either of those works, they're the exact same thing. So let's go ahead and put in values. And what is our omega again?
500.
Bingo. So what is negative J over 500 times 8 microfarads? 50.
Was negative 2.
And then what about L? Everybody agree with that? Everybody in agreement? So. Also, I should have read the question. I didn't even do that. I don't follow my own advice. So we said generate the sinusoidal steady state expression for the inductor current I4 of t in the format of that, where omega is radian frequency. Oh, it even told you 500 radians per second. And then I4 magnitude is the magnitude or peak of I4 in amps, and I guess phi, a different phi, or phi. Is that phi or phi? Exactly. It is phi 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 phi. Is the offset in degrees. So we need to, well, I would recommend making this into one loop and then finding the current. And then is that current for this whole loop going to be the current that flows through this inductor? So this current, that main current, is going to flow down here. You can see that. But then the inductor current is going to go this way. But then some of that current is going to come this way too. Exactly. So first we're going to combine these two and find the big current, and then we'll current divide. So what is the impedance of R3? It's 100. R3, sorry. R3. So this one, 200, that one, 100. So parallel, it's going to be 1 over 100 plus 1 over 200J. Just combining those two in parallel. Making sure. I thought that the guy, I saw an email and I was like, did the guy like just give me the room? I was gonna be a little upset. It's okay. What we got for impedance? 30 plus 40J. That is a nice, huh? 80J.
Yeah, well, 80 plus 40.
80 plus 40J. That is a lovely number. That's fantastic. 80 plus 40J. So now how do we find the current?
This series is happening.
So we have 80 plus 40J, negative 250J, and 200, right? So what is that in series? Z total. Equal to that. And then what's our E again? What's our V? V slash E. So V is this sinusoidal source, right? And that's that same that we found at the beginning. So this is our voltage, right? So 10 phase angle 30. Yeah. Sorry, I combined these two in parallel. So I saw that these two values, so this resistor and this inductor, were in parallel. So I took our impedance for this inductor, which was 200J, and then I did the parallel formula for those two. That make sense? Yes?
No.
Did you get a different value?
Yeah, 200 divided by 8 plus 3. Yeah. or J plus B?
Oh, so I think that's what that, so very much the next difference where you put that I.
Yeah, the J.
Or you get a different result than.
Use the appropriate,
Right. Can you show us how you feel?
So apparently my calculator is.
Worry about problem setting.
I got 200 over take first to the word.
What you,
Probably get the direct to actually big.
yes.
In your calculator, is like when you multiply.
Yeah, so you need it to be this I right here. So that's a gross number. And so what I'm doing right now is I'm doing Control Enter, which is our approximate enter. So that is also a different answer than what you got. So it should be in degrees. Why'd you get a different number?
Oh, you did, instead of dividing by one, you just took the inverse of it.
It's the same thing.
I know it's the same thing, but I'm saying that gave him a different answer.
Rectangular,
I think you know.
yeah, I got 80 plus 40.
And you
Is that
did,
the right number?
and you did the one divided.
Oh, you
by-
might have to convert it to rectangular, maybe.
Yeah.
It,
Oh,
Yeah,
this is
it-
in phase angle. Oh, yes, yes, yes. I bet. There we go. Okay, cool.
Oh.
So they were the thing.
Okay.
So there we go. And I'll explain what I just did. Just wanted to make sure we were all getting the same answer. So we did the same thing, and you can even do it with this weird thing. But if we want to ever convert from polar to rectangular or vice versa, we're gonna go into menu. We're gonna go into number. Is that good enough? Can you kind of see that? Number, because it's a number. We're gonna go to complex number tools and then convert to polar or rectangular. So we get 80 plus 40i. Did you get that over there? You get the same thing, Jamie? Okay, are you tracking though? Okay, we can talk about it after a little bit if you want. Cool, so. Are you good with me using calculator? Okay, sweet. I greatly appreciate it. So now we have our voltage and we have our impedance. So how do we find the current? Yep. So we're just gonna take, oh, and then the other nice thing that is extremely important is knowing how to do that phase angle thing. So if we want to do 10 phase angle 30, what we need to do is we're gonna do 10. And then in our book, in this little book thing, I think it looks like a book. So hit the book and we have a giant menu of things. We're gonna want to go into this fourth tab. So we're gonna hit 4. And then there is this thing that is phase angle. So we're gonna hit phase angle. So now it's gonna give me an error. So no, it actually wants parentheses around it. It just, for syntax, it wants parentheses around it. So just, if it gives you that error, just make sure that's there. And then we're gonna divide that by this. I'm gonna also make sure this has parentheses around it. And we're gonna get another gross number. Oh, that's not right. Don't do that. So I got 111.803 millivolts, phase angle of 3.43. And we can also go into, if we want to do rectangular, is slightly different, but actually quite different. But now what do we need to do? Yes. How do we do current division? What is the current division formula? So we want IL4, right? That's going to equal times 3, but yes. So we want the component that we don't want. So we're going to do the opposite value. So we're going to do 100 over the total value. So that's the 100 plus 80 plus 40J. Also, I do not care if you write J or I. Or if you do a mix, which is I have a habit of accidentally doing. So, because, yeah, current is I. And electrical engineers were like, no. They have other variables that are the exact same, but current, they were like, no, current. Yeah. So what does that equal to? Calculator times 100 over 100 plus 80 plus 40. We agree? Are we in agreement?
What is the total, just 80 plus 40 J? Instead of at the one, since it's already like parallel. We don't have to add another one.
Oh. Oh, it should totally just be 200J. It should be,
Supposed to
yes.
be just that 80 plus 40. 80 plus 40. Isn't that?
No, so we, for the total resistance, this is weird for current division, we do not add them in parallel.
Oh, right.
Just add the actual components. So it's the component that we don't want, it's the resistance that we don't want over the total resistance numerically,
So it's just 100 plus
200J, yes. Plus 200J, good catch. So now, oh, that's such a nice number. That's crazy how that works out. This awful number comes out with 0.050 phase angle of 60. That is crazy. Because this inductor impedance, yes. We're doing this value plus this value.
For the total current.
So we used, oh, I didn't write it down. That's on me. It's in my calculator. It's I total is equal to 0.11163 plus oops, 0.006698 J. That's why I was like, that's crazy how it comes out to a whole number.
And where did we get that from?
Sorry, that was from, we divided, yeah, I'm sorry. I don't normally do that. Hang on, did I make a mistake? I made a mistake. Didn't I make a mistake? Did you? He's my sanity check right now. I think I messed it up. Oh my gosh, y'all. I messed up the total impedance. Look, I put in the parallel impedance instead of what we totaled up. Right? Did you do the same?
But I was, you got it wrong, so.
Tell me. I am very, very frequently wrong, and it's also a lot whenever you're talking in front of a bunch of people. So, okay. So, what we're gonna do, we're gonna cross out all of what I just did. So now we have this voltage, this is what we're gonna look at, and this resistance, and we're gonna say that I total is equal to 10 phase angle 30 divided by 280 minus 210J, which is equal to, make sure I did this right again. I just did that. We're going to do the approximate value is equal to 20.02857 phase angle 66.86. So that is the total current. Now we're going to do the same thing I said before. IL4 equal to that I total times 100 over now 100 plus 200J, which is equal to a less nice number. Quite unfortunate.
Yeah, that's the same.
Okay, now sanity check. We're good. So I4, yeah. So now we're not quite done because it says that we need to put it back in terms of cosine. How do we do that?
Plug the number.
We're going to say, okay, this value right here is A, and this value right here is phi. Both of them. So what we're going to do is we're going to go over here. We're going to say that it is 0.012. Y'all can't see that. 0.01277 cosine of what's next? 500T, like I said, never changes. Plus 3.435. That is our answer. Now we're done with that one. Not too bad if you don't make a million mistakes like me. But also it's okay. I'll follow your process if you document it and keep doing it and you show that you did the current divider. I won't take off that much. It's just a calculator. Just make sure you say what you're doing. Make sure you write out this current divider formula. Or if you say current division, actually still write out the formula. Yes.
You saying I got the R, B 28 is the minus.
Yes. So I simply said this is in series with this, which is in series with our equivalents. Exactly. Do you have any other questions? Good stuff. Okay. Don Lane finally emailed me back. Said, I'm sorry, I have been dealing with a number of emergencies on campus. Ooh. So it's okay. Sorry, I talked for a really long time. My reviews go on forever. I hope that they are helpful. What was it? Huh?
What kind of problem was it?
Oh, that was a complex emittance. It was a steady state. Yes. Now we're gonna go on to our switch problem. This one asks for a bunch of stuff. This one, very much read the question.
Switch question.
I do not know.
So the homework, like I said, we just asked for, just be the parent.
He is gonna ask for the table. I talked to him earlier and I was like, hey, so you didn't put any of the homework, the questions on the homework with the table, and he was like, crap. So he said definitely go over the table today. Why we're gonna do it. It's not hard, it just has one extra step, but y'all can do it. It's easy. So actual problem is on a different page, but we're gonna read the question. So the RL network in figure 3 on different page has been at rest for a long period of time. At time t is equal to 0, switch is thrown to point B as indicated. Do the following. Calculate the values for the inductor current, inductor voltage, and the network. Basically, just fill out table 3. Next, apply and generate the fully written time domain expression. We're not going to do that part. It says to sketch as accurately as possible. Well, you know what? I literally already did that. It was what I did like a minute ago. It's basically asking for you to do this, but he won't ask you to do that because he hasn't really said that. So don't worry about that, but I told you earlier what it all means. And then calculate the value of T1, where the inductor current is 0, and then calculate the value of rise time. So let's write out a couple equations before we start. So this is asking for the current at 0 minus 0 plus and infinity, along with the voltage at 0 minus 0 plus and infinity. And this is an inductor problem. So, and then it also asks for the tau. So what is the time domain expression? Inductor, sorry. This is what the circuit looks like. It's just on another page. IL infinity, right? I'll even see that. IL infinity times E. Yes. So that is what we're going to write. And then what does this mean? How do we find a value whenever it's equal to 0?
Find T, ILTC 0.
Yeah, we just set it equal to 0. We just set the thing that we just solved for equal to 0 and solve for this T. So just set equal to 0. And then what is the formula for time rise?
That's one time.
Easiest equation, I think, in this entire class. It is tau ln of 9. Great. And so, whenever you're doing these problems, write all of these things out. Even if you get all the numbers wrong, the fact that you know that these are the equations lets me give you points. Since it is worth 35 points, this question, a good bit, like obviously 5%, I could give you 2 points for writing the equation. I would probably, I'd give you 1 point, and then if you used your values, like if you solved and used your values, but it was wrong, I'd give you another 2 points. So you'd get 3 points, even if you got the wrong number. If I see that you did things wrong, but you had right steps, I'll usually go in with my calculator and solve what y'all did. And so if I see it was just a little error somewhere, like a rounding error, I'll write rounding error, and then pretty much. Please don't round. Please keep 3 or 4 decimal places. And maybe I'll take a point off. Because I've told you so many times. You gotta have repercussions at some point. But then if you apply your values into this formula, I'll probably give you half points. So I would give you 5 points. Because it just says use the values to write the time domain expression. If you used your values to write the time domain expression, I can give you points. So easiest part of this. So we're looking at an inductor. Are there any easy values that we can fill in here?
Yes.
Exactly. After a really long time, an inductor looks like a, because I don't know if you've seen an inductor. It's just a wire wrapped around in a circle. You can make, I got to make some like a, what was it, like an LNA, and it was just like PVC pipes with like, probably like 4 gauge, no, it wasn't quite that big. It was like 10 gauge wire, 8 or 10 gauge wire, and we just wrapped it around like 8 or 9 times, and that was the inductor we used. And so after a long time, it's a wire because it's literally just a wire. So is there any voltage over a wire after a long time? So 0 minus, we're just gonna write 0. At infinity, 0. Boom. Easiest points you can ever get. I'm starting to sound like Russell. So from here, what we're gonna do is these questions, they have switches, but at every point, it's just solving another circuit. You do the switch, you redraw the circuit, and you just solve for the voltage or current how you normally would solve a circuit. So for this one, let's redraw it for time is equal to 0. Is this in the circuit? Is there any connection here at time is equal to 0? What about that?
No.
So do we agree that the circuit at time is equal to 0 is just this little bit?
Yes.
Okay, let's draw that. I say don't draw it if you don't need to. These guys are the ones that it helps redrawing the circuit every time. Because it changes a lot. And oops. Especially on some of these, it gets a little funky what you have to end up doing to solve them. I don't think this one is too bad, but I didn't actually look at solutions, which is probably unwise on my part. But I'm sure we're going to be fine. So, oh, this one's going to be great. So after a long time, we said it acts like a wire, right? So we're just going to draw a wire here, right? Because I'm dumb. It doesn't exist. It's just another wire. So there's just a wire and we're trying to find the current flowing here. It'll be IL of 0. What happens whenever there's a wire in parallel with the resistor? Does any current go through that resistor? Because why would current go through something with essentially infinitely more resistance than 0? It wouldn't. So turns out this also gets canceled out at 0. So I was saying this the other day because I didn't really even think about it. If you ever see a wire in parallel with anything, it's gonna go away. It's not gonna.
Even if the inductor was never there. So,
I literally just like an actual.
So like literally, if you ever see a wire in parallel with a resistor or a
current source.
current source, it would
They both.
short over a battery. I think Turner has drilled in your head that that's bad. Don't short a battery.
Yeah.
Financial time. Very briefly, probably.
Yeah. So don't short stuff. If you see a wire in parallel with something, goes away. So this turns into like the easiest circuit ever of battery, a resistor, and a wire. Right? I mean, yeah, you just find the current, right? And what is that? 2K? So what is the current flowing? The current's going to flow in this direction, right? Nine over 2K is equal to 4.5 milliamps.
Negative.
Yes. So I was going to say, so we're trying to find this IL going this direction. But we just found that this current is going in the opposite direction. So the current flowing in this direction is the negative of that. So it's going to be negative 4.5 milliamps. Now we're going to go over here and we're going to write negative 4.5 milliamps. So from 0 minus to 0, does that current change?
No.
Exactly. Because a inductor resists change in current. And then the same is true in the opposite for a capacitor. Capacitor resists change in voltage. So these two values are always going to be the same. So now we need to find well, we're going to go ahead and redraw this circuit for time is equal to 0/infinity. And to find, this is the trickier one. We need to find the voltage at time is equal to 0. That's the only time where it's going to have a voltage immediately when it switches. Because it resists change in current, it can instantaneously have a voltage over it. It's got to give somewhere, otherwise it would blow up. So for here, since we're telling you and you're saying it has current flowing through it, we can replace in the circuit it with a current source, right? That makes sense. Okay, so let's go ahead and draw it with this inductor as a current source. So we'll have resistor, and then what changes whenever this goes to 0? Does this still exist? Sorry. Is it connected to anything?
Oh, no, no.
So that's going to be what changes. So our network is going to end up looking like this with a current, actually it's first. So it's gonna be 4.5 milliamps. Which direction, up or down? So we said that the current, oh wait, I totally lied. It is up, you're right.
Oh, is it?
It's, so we said that this current going down is negative. That means that the current source is going to be pointing up and be positive.
Oh, we use the previous number.
Yes, because
State that.
this is time is equal to 0. We are going to put this current source in because it's not literally a current source, but it acts as a current source because it's going to be supplying current to the circuit. Go ahead and write in 1K, 2K, 3K. I love it. 10 milliamps. So how do we want to solve this? We can solve it however we want. Yeah. Yeah, I would say that's a good way to do it. Y'all see what he's saying when he says transformation? There's two currents that are in parallel with two resistors. A good rule of thumb is if you see current source in parallel with a resistor, think, I can transform this. So let's do that. In my head, I was like, oh, you can do name. That's so much simpler. Name would work. If you are like, I know how to do name, I know how to do main, and it works, do it. If you are like, current division makes sense, do current division. If you think, oh, transformations, immediately what my mind thinks of, do transformations. On these, do whatever works for you that you can solve the circuit. So 10 milliamps, V equals IR. So current times 10 milliamps times 3K, what's that going to equal? 30 volts. And that's going to be, where's that resistor going to go? We're still going to have this 2K. If there's a resistor on the bottom, so many people have done that on like either their resistor combination, they forget a little resistor at the bottom. Make sure you remember all your resistors. And then what's this one going to be? So we are trying to find the voltage. I did it again, didn't I? I'm thinking because, so we're not trying to find IL, we're trying to find V.
Oh,
See where, so we just transformed this. That's kind of problematic. Because we're trying to find the voltage from here to here. And I don't think that that is the same as 4.5 volts, because that would be too convenient. Is it the same as here to here? I don't know. I think it might be. I think it is. I think it is because think about it, right? The voltage drop over this is going to be the same as the voltage drop over this. And there has to be the same amount of voltage drop from here to here. So I'm pretty sure it is the same. However, should probably use a different one. Or we can do current and we can do current division, but that's weird too. What do y'all want to do? Y'all want to try to do name? Do y'all want to try to do see if it works? Yeah. So if we were to find the voltage here after this was transformed, how would we go about doing that? What do we think? We know the voltage drop from here to here is 4.5, right? But we need the voltage drop from here to here. Can we add anything to find that whole voltage drop? Can we add the voltage drop over this 1K?
Yeah,
The total voltage? Right? The voltage drop from here to here is the same as those two added. Okay. Then how are we going to find the voltage over here? Just Ohm's law. We need to find the current in the loop. And then we multiply that current times that resistor. I'm going to make sure that that works. I am pretty sure it works, but I'm going to verify before we get too far into the problem. Because as we have seen, I make mistakes. Remembered, I texted myself the solutions for this exact reason so that I wouldn't have to open up my computer. What do we get
75.
when they're added together?
Yeah.
It works.
Yes.
Sweet. That is what I like to hear. It did work.
Okay. Need to be careful.
So look, this resistor got put here.
Oh, I didn't see that from here. Okay.
Oh, sorry, that's my fault.
I didn't see it. I was wondering where it went. I'm like,
Yeah, that's my bad. But sweet, so it does work. So the voltage drop over this 1K is equal to what, 3.25? Question mark? What? Oh, okay, yeah, 4.25. So the total voltage IL VL. Come over here, throw that into here, 8.75 volts. Sweet, just got one more current to find, and it's the exact same as, well, sort of, very, very similar. And we're gonna draw it again. Made a proper mess over here. So we're gonna redraw the circuit one more time at time is equal to infinity, which the only difference between what we just did and time is equal to infinity is instead of a current source, this is a wire again. So source. This goes away. I'm trying to find this current again. How do we do that? You can do current division. So you can find and to show current division easier, do we agree that this, since this is a wire, can be pulled up?
Yeah.
So we can actually say that, yes. So this is the 2K, not the 1K. So we can do current division here. Or we can transform that back into a voltage, which we already know what the voltage is, and then just do Ohm's law. By and large, people don't like current division. Both work for sure. If we did current division, it would be 10 milliamps, so that's the total current. If I write it times 3K over 2K plus 3K, which is equal to 3/5, which is what, 6 volts? 6 amps?
Yeah.
6 amps. And then if we did it the other way, so if we transformed this, we already said it's 30 volts. And I'm just going through this because we already technically did this. 30 volts, 3K, 2K, 2K. So then I is equal to V over R, it's equal to 30 over 5K, which is also equal to 6. So proof that both work. So we're going to come back over here and do 6 amps. Oh, yes.
So, people do have a wire in front of the reason why they're not that one.
Yes. So if we so this wire is directly in parallel with this. Is that wire in parallel with this guy? So this becomes a wire, but it still is just a wire flowing to an extra resistor. Yeah, of course. So now,
I guess it's that's really.
gotcha. So I say question again, is this wire directly in parallel with this resistor? So because there is resistance going here, the current does get divided. If you think about it that way too. Yeah. And so now we got, the only other thing we have in here is tau. So to find tau, I forgot to write the equation for tau. What's the equation for tau? R for an inductor, which also is RC if we have a capacitor. Because I don't know if he's going to give you a capacitor or inductor question. But it's a tricky one for finding resistance. It can be. This one isn't too bad. But what we do is we're going to, wherever the element is, I was about to say, yeah, yoink it out, yank it out, and put terminals. And then it becomes a resistor combination question to 2 terminals, like all of the other Russell problems. What we do is we take this, and then we make terminals A and B. And then we're gonna redraw the circuit. And also to find that, we're going to turn off all of the sources. Also, we find the equivalent resistance after the switch. You always do it after the switch flips instead of before the switch flips. Does that make sense? Why? Yes, no, maybe so. So, the equation, right? The equation that we're looking at, if we come back to our little equation, is this the equation for before the switch or after the switch? Is this the, like, response? It's the response to the switch being flipped. So the equation is gonna depend on the new resistance, yeah. The new time constant instead of the old time constant. So that's why you're always gonna do it after the switch flips. So we'll come back over here. We'll draw it one more time, except instead of a wire here, we're gonna have terminals. And we turn off the voltage and the current sources. So in this case, what does this end up being? Mhm. 0 amps, no current, no wire. So it becomes just that first resistor. And then the switch is flipped, so that goes away. That goes away. So then it's going to be a resistor down here. Then a resistor here. Terminals A and B. You can't see that. Do we all agree with how I drew this? We got 3K. What is the first step? How do we simplify this? And remember, with simplifying, always go from however far away from the terminals you are. Don't start at the terminals. Start like terminals are on the right, start at the left. These are in series. Gonna be 5, exactly. 5K.
Might be fine.
5, 6. Cool.
Oh, is it 6 milliamps, not 6 amps?
Yes. Milliamps. Good catch. So now it's that divided by L, which our L is 680 microhenries. So it's 680 microhenries divided by 5 over 6K, right? Or is it just 5 over 6? Is it 6 over 5?
No, it's not, it's a column. So here. Here's 5 over 6K.
Okay. 2. Also, I don't know if this trips you up. It tripped me up for a long time, remembering milli, micro, nano, pico. I'd write it down. If it trips you up, write it down on like your cheat sheet.
That's right.
So right, milli is -3. Micro, which is the mu, -6. Nano, n is -9. And pico is -12. And then you don't really get to femto, but femto is -15.
Yeah, I don't think we ever use that.
The only time you might is in passive and active.
Oh, yeah.
But what we got for our tau?
If it's
Also, for my sake, please write it in the table. It makes it a lot easier for me. Okay, so now, first 14 points, done. Next, what do we do? Just plug it in. IL, what's IL gonna be equal to? Plus, tell me what to write, come on. E, the negative T over 816 nanoseconds. Sweet, 10 points, boom. So now what we're gonna do is we're gonna set this equal to 0 and hit solve on our calculator. Because I mean, I guess it isn't horribly bad, but it's not great. Also, I don't care if that's not a decimal. I don't care if you simplify this, and I honestly suggest you don't, just because the least amount of math that you do in your head, the better you're off. So just hit solve for T. Y'all remember how to solve in your calculator. I think I'm gonna go over it again in case folks at home. So we're gonna do menu. We're gonna go back to our menu. We're gonna go algebra because solving is algebra, and it's the first thing. Menu 3-1. So we're going to type in our equation. So 6 e negative 3. That's how I do milli, is e negative 3 instead of times 10 because it's clunky. And the e button is just right there. That's how I like doing it personally. Plus negative 5 e negative 3 minus 6 e negative 3 times e to the negative t divided by 816 e negative 1. Yes. And set that equal to 0. And then comma, what you want to solve for, t. T is equal to 464.381 nanoseconds. I suggest keeping your calculator in engineering notation. Engineering notation just means it'll spit out multiples of 3. So it'll spit out milli, micro, or nano. I think I did that for you in your calculator, which is why I did that. So can you even read that sort of? 464. So T1 is equal to 464.381 nanoseconds. I would prefer whenever you're looking at seconds and really, really small, if you do put it in nano or micro, if you put it in times 10 to the whatever, that's okay. It again makes my life as a TA easier, and I would greatly appreciate it, is what I'll say. And then lastly, rise time, TR, what does that equal to? 11 of 9, 816 times ln of 9, 15, 9 times ln of 9 equal to 1.792 microseconds. Please box your answers. Again, makes my life so much easier. And we're done with the switch problem. It's a lot of work. If we wanted to draw out the thing, how would we do that? I don't think you're going to have to, but the question asked for it, so why not? Right? So let's take this as an example. So we said that tau is when you get up to 60%. We're pretty much just gonna, it's always gonna look, I lied. I totally lied. So the beginning and the end are gonna be your 0, minus, and infinity. So you need to start at your 0 minus, which for us is going to be negative 4.5. And I'll just kind of do this one. And then we're going to go up to 6. Right? And we're just going to kind of do up like that. And then we're going to say that so tau is 860 nanoseconds. So I'm going to say about like 60% up is like there. We're going to call this 816 nanoseconds. And then the time to get from 10% to 90%. I'm going to go up here. And I'm going to do one of these guys. And that is going to be TR of 1.7929. Like that. That's what it would look like if you drew it out. Just kind of interesting. That's like if you did it on a scope, that's what it would look like. Okay. So, does anybody have any question about switches?
Summarize the table.
Yes. I don't know what you mean by summarize, but I can try. So this is looking at your current. So this is your current at 0, minus, 0, and infinity. Otherwise, before the switch, after a long time, at the time of the switch, and after the switch has been flipped for a long time. Same for voltage. Right before, at time, after a long time. And then tau is your L over R. Yes.
Can you back to the page where you can? I did that back.
This, and that one, I think, needs to be put in, right? So it's not just needs to put that.
Correct. Yes, that is a big benefit of doing it in here. So. Yes. Yes. Are you just taking a picture? Do you have a question or? Oh, you're good. And then a little more voltage for an inductor. After a long time, there's going to be no voltage. So it's a Y. So those are zeros. The current from 0 to 0 plus, it resists change in current. So it's going to be the exact same.
The inductor resistance change. Current.
Yes. 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 How do you feel about that? That better?
Yeah, I'm just kind of curious as to why it's negative.
The reason it's negative is I have a million pages.
It's the current of the. Current of the inductor.
So it's the current of what we defined the current of inductor is. Why on earth did I make this? Oh, it's right in front of me. So look at the direction of this battery, right? It's going to be pushing the current around this way. right? But we're telling you, this current is in this direction. That is defined from the circuit. So because of that, and because these are opposite directions, it's night. And because it switches from negative to positive, that's how you have the one, whenever it's at 0. If it didn't switch from negative to positive, it would never equal. Okay, cool. Any more on switches? Really, really quickly take in the problems on your problem set. They are tricky, work together, ask questions. Some of them you have to redraw them in really weird ways. We've been doing them in IEEE, and they've been a little rough, and I know that. Take them in, and then on Tuesday, the solutions will get posted. Study those if you got them wrong. Have them open whenever you take the test. You had a question?
Yeah, I was kind of especially, on the next one.
This?
8.75.
Yes. Yes. Okay, so what I did is we wanted to find, okay, we did some interesting stuff. We said we're trying to find the current over the inductor. And the inductor is that current source. We replaced the inductor with the current source because it is supplying current. It's not going to change current immediately. So from here, we're trying to find the voltage over the inductor. What we did is we said it would be really easy to find current and voltage if this was just one loop. And we realized that we could combine these two and combine these two to get 2 voltages. From there, we realized we need it from this node to this node. So it's not just this voltage. It's not just this voltage. It needs to be the voltage from up here to down here. Because that is what this means. It is the equivalent from both of these. And on this also, the current gets divided out, but 2 things in parallel are always going to have the same voltage, right? So that's why we can just say, okay, the voltage between the top and the bottom is the same as the voltage across the resistor and across the current source. So we combined them. We found the current, which I didn't write down. I don't remember what the current was, but we did essentially 30 minus 4.5 to find the total voltage, and we added 3 plus 2 plus 1K. We divided, and then defined the voltage from up here. I'm covering it, but from up here to here, we just kind of, I guess, superposition it. We say, okay, we know what the voltage over this is, and with the current, we can find the voltage over this resistor. So if we know both of those voltages, we can add them up. We know that this one's 4.5, and we found that the current times 1K is 4.25. So I guess it was 4.25 milliamps. Yeah, that makes sense. And so then we just added those together, and it's 8.75. Better? Sweet. Anything else before we get to second order? Where none of us are happy. Okay, so Russell is going to do a review on second order in class as well, because he knows it's a little rough. And it's not gonna be, so full transparency, he has not tested second order since 2021. 2021. This is, I was a little surprised when he said he was gonna do it. I don't know if you heard me at the beginning of the class. I was like, you don't want to push it to the final. He was like, no, I think I want to do it in this class. But the bright side is he's not going to teach any more than second order until the rest of the semester. You have pretty much learned everything that's going to be on the final exam. You're just getting an extra exam on the same side. So double-edged sword. You are gonna have a bit of a tricky exam, but then your final, you should feel a little more confident. So we're gonna do this. And like I said, he's just gonna kind of be looking for damp. And we're gonna do it a slightly different way than this one. And I'm sorry, because I know you literally just took a picture of this one. Yes. So oscillatory means undamped. This is the same thing. Underdamped, he didn't ask for, but we're gonna solve it because that's probably what he's gonna ask. So, this is an ODE. Have y'all been learning ODEs? Do you remember ODEs at all? Sort of, kind of, from math class. So, from this, we are gonna kind of pick up some key information, some nibbles of information. This, and this are that are always gonna be there. It's always gonna be derivative times the VC of t plus second derivative of VCT. It's like saying that I'm signed in. It's the worst thing. Like, hello, and it doesn't, not saying hi. But the things that are important are the coefficients in front of them. So this, and that are gonna be our A. It's weird. This is our A3. This is our A2. And this would be our A1, which here A1 is equal to what? That's an A. So from here, and I'm gonna have the chapter Z1 open because I am, again, full transparency, shaky on this. You do it in circuits too. This is genuinely helpful. It's not like we're testing you over stuff that you're never going to use again. Damping ratios, omega n and zeta, which are in Z1, but we're not quite getting you to like zeta and omega n. That is so much of circuits too, and it's so much of controls, and it's stuff in things like robotics. Zeta and omega n are so important. So don't be all insanely frustrated that you're getting tested over this and it's not fair. Is it slightly unfair? Maybe. But it'll set you up. It sets you up in a really good spot. From here, what you're going to end up doing is you are going to be, step one, finding the zeros of this equation. You're going to find zeros. You have a question?
Yeah, I can't. That first piece, the with, A1.
No, so the value next to it,
Oh,
so the,
whatever we're calling it.
coefficient, yes. The coefficient is A3, so we can go ahead and write that. So A3 equal to, wow. Oh my gosh, I stand corrected. It's 20 times 10 to the negative 18, which I think is, it starts with an A. Yes. That, atom, ATTO, right? Yeah, that's 10 to the negative 18. But then A2 is gonna be equal to 900, and I'll just keep it in negative in this form. Negative 12 plus BF, and A1 is equal to 1. So now what we're gonna do here is, this is essentially well, it is an ODE, but we can make it into a little bit easier by just saying all of those derivatives are X, but we're gonna call them P. So we're basically gonna say A3P squared plus A2P plus A1. From here, we're gonna find the zeros, which that is going to be your P1 and your P2, right? We're gonna use the quadratic formula, which I don't know if that was properly drilled into your head in like high school, or if y'all remember that at all. And then what we also need to do is we actually need to normalize. We don't want this to be here. We don't want this. That's you don't want the A3 to be there. And this is because of how I'm trying to figure out how to word this. The definition of where the damping comes from is from the quadratic formula. And it's that square root. So that's what we need. So we need to make sure that there is no coefficient. And that's because the quadratic formula is all over 2A, right? But if there's an A down there, then it's not in the discriminant anymore. So we need to normalize it by dividing. Like I said, I want to make sure that I don't mess this up. It is.
And before our because that this is actually that is the line that
So this is gonna be equal to, like we said, it's still what it's equal to. 10. So first up, we're gonna normalize it. We're gonna divide everything by A3. So we're gonna divide this by A3, and we're gonna divide this by A3, and we're gonna divide this by A3. And we're not gonna write in values because they're kind of gross. So we're gonna have squared plus A2 over A3. I'm just rewriting the same thing. Plus 1 over A3 From here, we need to apply the quadratic formula. No, we're gonna find the homogeneous solution. And the homogeneous solution is whenever it's equal to 0. So that's the not particular. Particular is whenever you actually have values, and that's when you're gonna have an equal sign. So we're just gonna say that this is equal to 0 right now. And we're just going to plug in the quadratic formula, which is much easier. So do y'all want to do quadratic formula? Yeah. That's very good. Mhm. Mm. You know? Yeah.
Divide by 8.
Yeah.
Yeah. But you have each divided by 8. Divided by 8.
No, it's not, A3 is squared, P is squared, it's like if it was 4x squared, and you divide by 4.
Yeah, so if you divide by 4, then y is down on the 3.
Which one?
That is what, yeah, you want 8 squared, so it's 8 divided by 8, so which.
Oh, that was me doing it in the moment. That was-
That's when we divide.
Yeah, this was just me rewriting it. So those aren't actually, I see what you're saying. This is the solution. So what we're gonna do, so quadratic formula is b plus or minus the square root b squared minus 4ac, which a is 1. Is it negative b? It's negative b. You're right. All right. But the nice thing about this is determinant is discriminant. B squared minus 4ac. C is 1, so we are going to work with b squared, which is a2 over a3 squared minus 4 times a1 over a3. This is the big thing that we're going to look at. That is like the thing. And I've been digging around in here because there's a table that shows the damping. I do not have it memorized of when it's over a certain amount. And that is all in chapter Z1. I know, I'm sure Russell did it. I'm sure I've pushed it.
We can just put those values in the calculator and just solve like this.
Yes.
Yeah.
Yes. No, 100%. So here's our table. And like I said, this is straight from Z1. So this is the big thing that you're going to look at. We're going to solve for P1 and P2. Well, there's multiple ways to do it. If you solve for P1 and P2, this is you actually solving the zeros. If you solve the zeros and they are two negative, real, unequal roots, it's overdamped. They're negative, real, and equal, critically damped, complex conjugates, underdamped, imaginary conjugates, undamped. So I'm confused about. You went over this in class. Do y'all? So let's, you know what? Let's look through and try to understand Russell's. So this is talking about the discriminant. Let's just brainstorm this together. That's what we're gonna do. So this is talking about the discriminant. There's two terms in all of these. And it's saying basically if the first one is equal, greater than, equal to, or less than. This comes from his example of this was his discriminant. The first thing was the B, and then it was minus the second term. So you're so right. I'm so dumb. So basically, it's setting them equal to 0. And he resolved A2. He,
For the equation, equal,
mhm. So hmm. It's,
a lot of them.
y'all haven't gone over this.
No, we did, it's just. It is, yeah, that's, we haven't went over it today. We give one example for like critically damped, over damped.
These are brutal. These are brutal. Mhm. So let's solve the roots. Let's start with that. Without the doing the discriminant. What are the roots of the equation that we made? Someone who graciously loans their calculator. Do you want to plug in?
So,
So we're going to put in negative A2 over A3. Is it?
For inside the square root, I got negative 1.97975 times 10 to the power 6.
Okay, so that's the discriminant.
Didn't put CL.
Add
We would need to find.
Yeah, you need to have CF in there.
So
You're
we should
so.
find critical bad density equals 0.
Mhm, mhm. So we're gonna set. We're gonna equal to 0. We're gonna do, that's with B squared. So that's what you're saying. Just gonna write this out. So this is actually what it is. So it's 900 times 10 to the negative 12 plus CF over 20 times 10 to the negative 18 minus 4 times 1 over 20 times 10 to the negative 18.
So CF got two cases.
Mm-hmm. What are the two cases?
One is negative 9.844
Mm-hmm.
times 10 to the power negative 9,
Mm-hmm.
or 8.044 times 10 to the power negative 9.
And did you set the discriminant equal to that or the whole equation?
Just the discriminant.
Okay. So what he did is he did. Okay. So we have two values for CF. And they are, my computer just died. This is, second order is going great, y'all. Like I said, I am sorry. What'd you say there were? They're right.
Negative 9.844 times 10 to the power negative 9.
9
The other
and
one is 8.044 times 10 to the power negative 9.
sweet.
Wait, man, what, how did you do that?
I'm still like throwing it. I'm not sorry about it.
No, but well, I'm saying like, why, I guess I'm not considering you guys.
Oh, but yes, the CF is in the square.
Okay.
Yeah, and if you do it by hand,
Oh,
you
so
just put the CF right to get the other side. Yeah,
Okay.
it's in that square root.
So the
So
first you saw the CA, you put that one back on. It's.
Okay, okay. So from here, what we're gonna do is, yes,
we're pretty.
so what we're gonna do is we're gonna plug this in. We're gonna take this and we are going to plug this into A2. Because that's what we're trying to solve, right? That's what had the A2 in it. That's what had the CF in it. So we're gonna plug that in and then we're gonna figure out what the new A2 is for the positive root and for the negative root. And then I'm just for ease of calculator. So when it's 8.044, A2 is going to end up being 447 times 2, 7.2 times 10 to the 6. And for the other one, it is going to be negative 447.2136 times 10 to the 6. So this one is obviously less than 0. And then the other one is greater than 0. So, okay. Makes sense. So these are equal magnitude plus and minus. Whenever it is less than 0, it is going to be undamped or oscillatory. If it is greater than 0, it is going to be critically damped. So for
It was I put the first one. Maybe.
the positive one.
Okay.
I thought, oscillatory was underground.
It's under.
Undamped.
Oh,
Mm-hmm. Is so, and this is going to be proven by this. So whenever they're equal to each other, they're negative, real, and equal. They're just conjugates. They're not complex conjugates.
They just know. Underdamped.
I don't think we can actually, because it already tells you what it is and it tells you what it's equal to. No, that's something. Straight in. You can tell. Now what we're gonna do? We're gonna go through the homework problems and we're gonna do the same thing. What?
Yeah. And then it's like.
But still,
Yeah.
Same thing as in we're gonna like look at the solutions and work our way through.
just that's bad.
Exactly. Basically.
we're gonna work backwards because I don't know how to help. And so that's what we're gonna do. Okay. Start out. First question, right? Let's do, 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 do. Should I? What do you think I should do for the recording? Keep going. Okay. So we have this. We're gonna do the same process of finding the roots, finding the discriminant with the quadratic formula. So we're gonna do that same thing, just this is A1, A2, this is A1 equal to 0. This one's simpler.
You explain like what the problem is asking for the.
Yes, that is a great, it's a great idea. So this is second order, right? Realistically, these P's are derivatives. It is using a constant K as an active variable used to control time domain characteristics. Considering only positive values for K, calculate its ranges within 0 to infinity, for which the response of V of t is overdamped and critically damped. So first, let's find the quadratic formula. Okay, start there. So we have -1, 2, minus. So I just did 1 plus k over 2 squared minus 4 times 4 plus k over 2 squared. And this is times 1/2. We have our basic thing. If we simplify this out, if we actually do the
Oh, okay.
I just divided by 2 on both of them. I meant to do it with a big brackets, but we're gonna simplify out this. We're gonna multiply out that. I feel that. Okay, so I'm just gonna tell you what this simplifies to. You multiply it out and it turns into a quadratic of k squared over 4. Are y'all fine with me just doing the k squared over 4 minus k minus 15? Makes sense. So this is the discriminant. Yep. And then what we're gonna do is we're gonna find the roots of this. So we're gonna factor this out to gonna factor this out and we're gonna yeah, sort of. We're gonna basically make this and then divide it all by 4. So it's gonna be a squared minus 4 minus 60 divided by 4. And then we're gonna factor out this. Yeah, we're gonna factor. Yes. I was looking for a different
X,
pen.
K is a minus 10. And K percent.
I was looking for a different pen. So our zeros are gonna be 10 and -6. But -6 is not positive. And we said only positive values, right? So we're gonna throw out the -6. So we see that our K equal to -10 is equal to 10 for critically damped. Because that is when you set it equal to 0. Yeah, and I can just read this. So this indicates that the roots are real and equal. Critically damped means, period, they are real and equal. That is the only situation.
I thought it was anything else better.
I can. Okay. Okay. So the roots have to be real and equal for it to be critically damped. So K is equal to 10. Okay. So the next thing is the roots. I don't know if y'all have chapter Z1 pulled up, but there's a table about the roots of the roots. And the way it works is if they are real, if they're real and equal, it's critically damped. If they are negative, it's going to be a complex conjugate and it's going to be underdamped. I'm going to write that down here. Complex conjugate. What page is that on? It's on page 20 is what.
Oh, it's a different.
Underdamped. And then real and distinct, which means that they're different. overdamped. Nope. So we're not gonna look at anything lower than 0. So our values are gonna start at 0. Okay. So up until 10, so that's when they're equal. From 0 to 10, it's gonna be negative, right? Because our k is k minus 10. So it's the square root of k minus 10. If it is negative, then it's gonna be underdamped. I see. I see. So whenever 0, and real and distinct is going to be overdamped. If the value is positive, what's the square root of a positive number? But they can be different a lot of the time. So pretty much anything over 10 is greater than, equal to, greater than 10, going to be overdamped. So that's actually all you need to do for this question. If it is, since it is real, it's only positive.
About pieces.
Mhm.
Yeah, it's like, tremendous larger than 0.
Mhm.
Equal to 0 is critically and then less than this.
Mhm. And that's, you can think about that with the square root. And that's what I just makes sense now. The roots are square roots, right? We know how square roots are gonna, okay. I have a piece of paper. So we are looking at roots. So we have b plus or minus discriminant. So that table, y'all are looking at the table, right? So if you look at those graphs, you're saying that they are equal. Then the only time that they're ever going to be equal is if there is nothing in that discriminant, because it's plus and minus. If that is 0, that's the only time they're ever going to be the same. So if it's equal to 0, then it's critically damped. If it is going to be positive, then a square root of a positive number is going to be a positive number, and then it's going to be plus or minus that positive number. That's why they're going to be real unequal values. And that's where you get, I need to pull up the chart. That one's going to be overdamped. And then if it's less than 0, that's bad. You're going to get imaginary numbers. That is when you're going to get underdamped. Yeah. So undamped is what we were looking at on the other question, where it was Or A. Or B. Oh. That makes sense. Okay. If this is equal to 0, though. Yeah. That's where it's undamped. So, or oscillatory. So if you're A2 equal to 0, it's going to be undamped. / oscillatory. I'm sure I spelled that. So that's making sense. That making more sense for y'all as well. That took me too long. So you know what we're gonna do? This is the answer to this. We can box that and be happy. So let's look at the next one. Let's just keep going through the homework. Yes, sorry. Pictures, questions. Cool, I'm gonna say it again. Y'all are good, my fault. So this root, let's look at this. If we do our roots, so we set this equal to 0 to find the roots. So we have the 4 goes away, we have k plus 6, k minus 10, so k is equal to -6, k is equal to 10. We are saying that there are no negative values. We said considering only positive values for k. So we ignore that. Helpful. But from here, we know that 10, k is going to be in the discriminant. Yeah. It's going to be k minus 10. We're looking for values of k. So we are looking from 0, k is equal to infinity. Can you see that? You can see that. From here, we know what I said over here. If that that discriminant is equal to 0. So if it's square root of 0, that's when it's critically damped. So if it's k minus 10, so k minus 10 is equal to 0, we know that k is equal to 10. That is specifically where we said it's critically damped. Yeah. And then if we're saying if that square root is negative, it's underdamped. It is less than 0, underdamped. I don't like what did this. So that's how we got this. And we know that if it's greater than 10, aka so clarified discriminant negative, discriminant positive here. Does that make more sense? Yeah? Okay, cool. Let's do the same thing on the next one. So similar looking, we're looking for the range of RM. So second order differential equation and initial conditions for terminal voltage of a scaled network is given below. So we have dVdt means our A3 is equal to 0, or 1, sorry. We have 5 minus Rm over 4, which is our A2, right? We have 2 minus Rm over 4, which is equal to our A3. A1. A1. Then it's equal to 2 times unit step function. Which y'all haven't learned what the unit step function is. That's not very nice. Which in time, it's literally just at 0. So at 0 goes up 1 and then is 1 for infinity. So at time less than 0, it's 0. At time greater than 0, it's 1. All he's saying is that it's equal to 1 whenever time is greater than 0. Except it's 2, because it's 2 times the unit step function, so it's 2 for infinity. That's all he means by the unit step. Where v of 0 is -1, and the ddt is equal to 5 volts per second. So let's focus on the first part. So we're going to do the same thing where we find the discriminant. We're going to find the square root. Let's go ahead and calculate that. So our square root is going to be 5 minus Rm over 4 squared minus 4 times Rm over 4. Just equal to, oh, I figure that y'all don't want to simplify that squared right now. Sorry, this is the third question. I don't know if I said that. We're gonna skip steps. Because I'm tired. I'm sure y'all are really tired.
Thanks.
Oh yeah, these seats are terrible. Just sit in junior in these for like 3 hours and I feel your pain. Okay, so we're gonna skip steps and I'm gonna tell you what the discriminant is equal to. This is equal to Rm squared plus 6 Rm minus 7 over 16. So
That was without the square root, right?
yes,
Oh,
that is what's under the square root.
yeah.
So factor it out. Rm minus 1 times Rm plus 7. 16. We're going to do the exact same thing. So for overdamped, set it equal to 0. Actually, let's do critically damped. Let's set it equal to 0. Like we said, or backtrack. I said it's equal to only a positive number, right? So we're gonna ignore. We're gonna ignore Positive. So then we have RM minus 1. So what's critically damped going to be? There's that equal to 0. And RM is equal to 1. Going to be critically damped. Now, let's have it. When is it? Well, less than 0 is going to be pretty obvious, right? Less than 1. If it's, we're looking at, for when is RM minus 1 negative? It's going to be whenever it's from 0 to 1, because once it starts being over 1, it's going to be positive. So when R0 is less than or equal to RM, which is less than 1, it's going to be underdamped. Remember how I said the unit step was 1 for infinity? I was thinking of the unit function, I guess. The unit step is a step. And then it's normally a unit step is up to 1 and then down.
That's all.
Yes. So since it's 2, it's going to be up and then up for 2. So our range is from 0 to 2. It's not from 0 to infinity. Which means that if it's positive, it's going to be from 1 to 2. So that's the whole range. Yes. Okay, I think we all need a break. Yeah. This is, I think, really what you need to know. It's on the table. It's a little, yeah. Yeah, and it's making more sense for me now. It was a little rough understanding at first, and I'm sorry.
You're gonna have to like make like the equation.
Instead to generate that kind of emotions.
Yes. This one did. That's not gonna be on your exam.
The generator.
Correct. Yes.
So it's just gonna be the,
Yes.
but this is not,
No, it's
so
not.
really, okay, so we're not really, we're really solving, but we're really like different range from what we saw, that was the range. Okay, that was the other,
Mhm.
well, like, but what's changed?
Mhm. So these are ones with variables. There are other ones where all you do is find the root. And then you say if that is under 0 or if it is.
They
Yeah.
said under the roof, for, but they're just different, yeah.
Mhm.
It's not, it is under the roof.
Yeah. And like I said, I'm sorry that took me a minute. And same with most of this, like dividing, even doing the quadratic formula. Do this all on the calculator. Don't try to do it by hand. Anybody have anything else?
You reading that chapter. See how to write it down.
I'm gonna go ahead and stop.